can convey those minutes some of the visions that we have for the technologies that we have been working on for quite some time now. This will have mostly most 30 minutes now we use self-introduction and some history, and then I'm going to talk about the vision for these accelerators and being different. So I spent a significant portion of my career, about 10 years or so, working as coordinator for a worldwide effort for understanding high-gradient accelerators. Really what happens when you apply extremely high electric field to the surface of materials, what happens there? And we know from very basic physics that around 6 volt lengths from electric field will evaporate atoms from the surface. However, from experimental data, we have been able to see that these things can break down at much lower fields than that, close to about 100 times lower than that, the surface erupt. And I don't care what sort of material it is, the surface starts to erupt at about 100 times from the theoretical value. Why? And with a little bit of work around from so many institutions, we started to form a picture, and the picture came actually experimentally. This is one example of this picture where you can see that the surface of copper that has the crystals of copper became very alive on that picture. And this surface was exposed to RF magnetic field only. And it turns out that the phenomena underneath all of this is very similar to a pin that you building back and forth until it breaks. So what happens is that when we expose the surface to a magnetic field that produces a huge current on that surface, one plane of the crystal of the copper gets damaged, the other plane does not get damaged, then your eyes can see the crystal structure of copper due to that. But based on this picture, we started to understand how to really build accelerators that can go to much higher gradients. And from that, we built so many different devices that once we understood what's really happening, we could structure the surfaces of our systems to allow for this magnetic field to be reduced and allow for the electric field to be enhanced and so on and so forth. And you can see some of the stuff that we have managed to do. One of them is, for example, is that we have been able to, in a bottle of electromagnetic field, get the field up to about 1 Tesla or something like that for interaction with electrons to produce lights. And another incarnation, we had huge deflectors that twists electron beams in free electron laser to see the structure in an attosecond scale for how the beam is being bunched and micro-bunched into this attosecond scale. But what we have is a vision for the future. And one of those visions is what we call cool copper gliders. What we want to do is to really create an accelerator that's about 10 kilometers long, that accelerates positons and electrons, smashing them together to study things like the Higgs boson. And this is about 126 giga-electron volt machine. And the Higgs boson is 126, the mass of the Higgs boson is 126 giga-electron volt. The technology itself is based on this new topology of the accelerator itself that allow the control of the electric and magnetic field on the surface so that you can tolerate this extremely high gradients that allow you to get this 126 giga-electron volt, actually being more than that a little bit, in a reasonable scale that does not span the whole planet, just 10 kilometers or something like that. Another idea that's dear to my heart and is very close to the work that I'm doing is that we're doing here at CXFEL and so on and so forth, is not to directly smash electrons and positons together, but use the electrons to generate photons like we're doing in CXFEL, and then take these photons and smash the photons together to produce the study of the hydrogen physics like Higgs boson and so on and so forth. The idea is that it will require only 600 meters of land, which is something that we have here in Arizona at some place, and really put the whole system together. It's cost effective. It's really it's a national project still, but nonetheless, it's the least expensive national project that you can imagine to reach the physics goals of the people are required to understand on the minute structure. What are we made of? What's the material? What's this matter? What is the material that goes with it? The only problem is that a few miracles has to happen in terms of laser optics and so on and so forth for this to be realized, but that's what makes it very exciting to make this happen. Of course, we have a vision for the light sources, and CXFEL, under the leadership of Bill, was the first adapter of our technology for accelerators and small machine, and it is up and running, functioning now. We want to extend this technology to superconducting materials. That's another vision that we are really interested in. And if that happens, and we can do it with superconducting materials, the accelerators and all this application around the world can reach a new level of the industry, medicine, security, etc. We have also a vision of how to do advanced computation to support all of these type of accelerators, and that's a new type of theory that really borrow from classical field theories that have been developed for many years, but never found its application in this field yet. We also want to miniaturize these accelerators that works at third-class regime. So instead of accelerator you hold in hand like that, it's an accelerator you can only see with a microscope. And we also have accelerators that we like to carry by hand and move around with big images and so on and so forth. This is all based on this technology. But the really dear to my heart vision is to build accelerators for cancer treatment, which is essentially you are zapping the tumor with very intense X-rays and treats through the body to kill the tumor. However, the vision that we have for this is machines that will do this treatment in under a second. Very, very small amount of time where the body becomes static during this process, so you can aim correctly to the tumor that you would like to hit. And one of my colleagues in the medical school at Stanford that I had collaborated with for a long time with this machine is going to give a talk here about all this work at noon today. Thank you very much.